The same disclaimer applies in that this is all coming from my memory, and so there may be some small errors in some of the details, but for the most part, everything should be the way that it happened. And certainly the physics should be pretty much the way that it's understood today. But we're going to start with the sun. So it's been known for quite a while, since the 1940s or so. There was a very famous paper, I believe this is the right paper, alpha, beta, and Gammov. Gammov with a W, but that's okay. So the alpha, beta, Gammov paper, I want to see if this is actually the one. No, this is the Big Bang paper. Okay, so well, anyway, so the Big Bang paper, alpha, beta, and Gammov. Beta was a nuclear physicist at Cornell, and Gammov was kind of a prankster type person, and so he actually included beta on the author list here, even though beta really didn't have that much to do with it. And so alpha, beta, and Gammov, because then it sounded like alpha, beta, and gamma. And so anyways, he did it that way on purpose. It was about the Big Bang nucleosynthesis. So this is not about how stars shine, but nevertheless, the same group of people or similar nuclear physicists were trying to figure out how the sun shined. Because it's not shining by burning, it's shining by nuclear fusion that heats up the interior of the star. And a consequence of the nuclear fusion from the interior of the star is that you produce a bunch of small microscopic particles called neutrinos. Basically what happens when you, in the core of the sun, is that you start with helium, you should start with hydrogen. Where's my pen stopped working? Okay, you start with 4 hydrogen and you convert that into helium. And you release a bunch of material when the helium comes off. You get a couple photons, you get a couple positrons, which is antimatter, and you get a couple of neutrinos. Neutrinos don't look like that, neutrinos look like that. That's the chemical symbol for neutrinos. So these are all consequences of the nuclear process where you take 4 hydrogen atoms, you convert it into this. If you add up the MC squared of the 4 hydrogen atoms, you end up getting more than the MC squared of all these things. So MC squared on the left-hand side is going to be larger than MC squared on the right-hand side, because then you get kinetic energy coming off of that, and you get these photons that are coming off of it. So as you convert this mass into energy, you form a more tightly bound nucleus, and you release all these particles. The photons basically immediately get absorbed by the nearby electrons, and their energy gets distributed around the inside of the star. The positrons quickly annihilate with the nearby electrons, producing more energy, and then it gets absorbed by the material in the star. And the neutrinos, on the other hand, neutrinos have a very, very, very small probability of being absorbed at any point in time. If you were to take a piece of lead, so like here's us on the Earth, here's your house, and you take a piece of lead, and that piece of lead extends all the way over to Alpha Centauri, so like the nearest star to us, so this is like 4 light years distant piece of lead, and you fire a neutrino through that solid piece of lead that goes from the Earth to Alpha Centauri, the chances are 50%, so it's a 50-50, that it will be absorbed, that the neutrino will hit anything. Neutrinos are so small, their cross-sectional area is so small, their interaction cross-section is so small, that only a tiny fraction of them will interact with anything. As a consequence, this is lead. Lead is more dense than the sun on average. As a consequence, the neutrinos that are formed in the center of the sun will leave the center of the sun and basically just stream straight out. So if you look at the material the stuff that's coming off of the sun, you have a few things. So here's the sun. Looks like this. Okay, it's a very happy sun. And you have stuff coming from the core. You have these neutrinos, and they come straight out. Okay. Photons, on the other hand, photons bounce around. So here's a photon coming out. It bounces around and diffuses out over the course of something on the order of 1 million years. It's not quite 1 million. I think the average diffusion time for the photons in the sun is something like 300,000 years, but that's like 1 million years. Okay, so several 100,000 years later, then the photons reach the surface, and then 8.5 minutes later, they hit the Earth. So photons, the information that the photons originally had with them has been lost in all of these random motions that they have as they diffuse from the center out towards the surface, and then they leave the surface. Then you also have the solar wind stuff just coming off of the surface of the sun that boils off And so the wind. So you have the solar wind, you have the photons that diffuse slowly outwards and then reach the surface and stream out, and then you have the neutrinos that basically just come from the center straight to wherever they're going. So if we want to understand or verify that the sun is actually shining through this 4 hydrogen goes to helium plus a bunch of other stuff, then the only information that actually makes it all the way to us is those neutrinos. The 2 neutrinos. So if we can make a detector that detects the neutrinos coming from the sun, then we can verify that yes, we understand the nuclear processes that are going on. And the nuclear processes are not, they're straightforward, but they're not trivial. So let's take a look real quick at what that is called. It's called the proton-proton chain. So if we look up the proton-proton chain, the proton-proton chain has its own Wikipedia page, therefore it's very important. And it looks like this. Okay, so this is the basic proton-proton chain. There are a bunch of branches to the proton-proton chain that will become important. Okay, so the basic idea is you take 2 hydrogens and you smash them together, you get a positron and a neutrino. That way it conserves lepton number. And then you take that deuterium and you combine it with another one, you get a gamma and you get a helium-3, and then 2 helium-3s combined together to form this. So this is the basic branch of the proton-proton chain. I do have a Wikipedia page, but I haven't edited it. It's just up there. The proton-proton chain is actually more like a tree. Let's see if it's got these different branches. PP2 branch. It's got this PP3 branch that has a different set of interactions that take place. That you can see it goes up to beryllium and then it splits apart. So you form these things, you combine it with tritium, you combine it again with boron, and then the boron splits apart, and then it forms beryllium-8, and then that breaks in half. So there's these different branches of the proton-proton chain cycle. This is the graphic that I was looking for. I think this comes from, I think this originally came from the John Bacall book. Is the CNO cycle anywhere in the proton-proton chain? So the CNO cycle, well, I'll talk about that in a little bit. The sun does not shine primarily through the CNO cycle. It does have a contribution, but it's not a very large contribution. The sun is dominated by the proton-proton chain. Stars that are more massive than the sun will have a different set of nuclear processes that they go through to shine. And we'll see that when I go back in a minute. So here's the proton-proton chain. There's basically 2 ways of forming the H2, so that's hydrogen deuterium. So this is deuterium. So you take 2 protons, you make deuterium. 99.7, of course, this is a British person that did this, and so it's got a comma instead of a period there. Anyway, so you form deuterium. 99.77% of it goes this way. You have 0.23% of it, so about 0.25%, where you absorb an electron in that process. So this is much more rare. But nevertheless, we can calculate the probability of this happening, and then we can weight them and get, what fraction of the system starts this way, what fraction of the system starts this way. But either of these 2 processes have you arrive at this state, and then it branches. So 85% of the time, it goes from here to form helium-3 and then helium-4, 2 helium-3s, helium-4 plus 2 positrons. You get 10 to the minus 5% of the time, which is, like 1/1000th of 1% of the time. Oh, this is percent. So this is 10 millionths of a percent, 10 millionths of a percent of the time. You get helium plus a positron gives you helium-4. And you get these neutrinos. The important thing here is that you get these neutrinos that come off of it. So there's a neutrino that comes off here, there's a neutrino that comes off here, there's a neutrino that comes off here, there's a neutrino that comes here at this beryllium-7 line, and there's a neutrino that comes off here, this boron-8 line. So the neutrinos are the things that we actually see from the center of the sun. And so what are we going to be able to observe? We're going to be able to observe the PP neutrinos right here. That's most of them, so that'll dominate the spectrum. Then we get this PEP neutrino, the proton electron neutrino. It's going to have certain properties as well. This HEP neutrino is going to have some properties, but that's just this branch right here. And then 0.1% of the time we'll have this neutrino that comes out, and we get 99% of this 15%. So 15% of the time we go down this way, and 99% of those is going to branch into this neutrino here, this beryllium-7 neutrino. So there's 1, 2, 3, 4, 5 different neutrinos, like varieties of neutrinos that are going to come from this. They're all the same kind of neutrino, but the energy properties of these different kinds of neutrinos are going to show up in the spectrum. And so I believe there should be, it's not listed on here. So we'll take a look at the solar neutrino spectrum that we would expect to find if this is actually how the sun shines. It turns out this is how the sun shines, but 50 years ago this wasn't known, right? So we need to make an experiment to look for these neutrinos and see if it matches what we would predict. There are other nuclear processes that are going on in the sun and in other stars. In particular, so the proton-proton chain is right here. As you change the temperature of a star, the temperature of the core of the star, then which process is important will change. So the CNO cycle is basically the same process where you're converting hydrogen into helium, except that you use as a catalyst something that facilitates the interaction is carbon, nitrogen, and oxygen. So if I briefly go to the CNO cycle page, we can see a diagram of how that works. It's right here. So this is the CNO cycle. You basically start with carbon, you start adding hydrogen, you get photons out of it, you get nitrogen, it decays, you get carbon again, you add something else, you get a different nitrogen that's not radioactive, and then you add that, you get oxygen, then that decays, and then you get nitrogen again, and then it comes back here. When you get to this nitrogen 15, then you absorb this and you spit out a helium. So there's your helium. You had 1, 2, 3, 4 hydrogens, and you get a helium out, which is exactly the same that we had in the proton-proton chain, except that, and this, whatever this is called, this nitrogen is going to decay back into the carbon that you started from. So this doesn't produce carbon, nitrogen, and oxygen. Instead, it takes existing carbon, nitrogen, and oxygen and uses them to catalyze these nuclear interactions. However, in order to get this nuclear interaction to take place, you have to be operating at higher temperatures. Okay, and so if the temperature of the core of the sun was a lot bigger than it is, then the CNO cycle would be more important. That would be the thing that dominates. So when you go to higher mass stars shine through the CNO cycle, provided that they're the later generation of stars that actually has carbon, nitrogen, and oxygen in it. But any star that's made today, and certainly any higher mass star that's alive today, is going to be on the CNO cycle because high mass stars don't live very long. And then the proton-proton chain, this is where the sun is. So you'll notice that when you switch the CNO cycle, a small change in temperature changes the energy output. So this epsilon is the total energy output. So this is 1 solar luminosity. If you increase the temperature, then you can drastically increase the luminosity of the star that you form in those cases. And then you can just take that and divide by something like a fraction of a percent of the mass of the star, because you convert something like of order 10%. That's not even 10%. You convert like 10 parts per million of the mass into energy. And so you can just take how bright the star is, divide by 10 parts per million of its mass, and that will give you roughly the lifetime that star will have. So so nothing can pass through a black hole. So neutrinos can't pass through a black hole. So this is the process by which the sun shines on the proton-proton chain. Okay, so what we're looking for then with this proton-proton chain is we want to see these different neutrinos that are going to be produced by the proton-proton chain. Okay, and that will show up in what's called the solar neutrino spectrum. Solar neutrino spectrum. So in the case of the sun is producing hydrogen, or it's converting hydrogen into helium, and so we're producing more helium in the sun. Eventually the sun will start producing different elements in it, carbon and oxygen, but that's basically where the sun peters out. Higher mass stars can go through a variety of additional nucleosynthetic processes to form things up to iron, and then when they explode you get even more, that's when stars explode is when you're going to get the really heavy elements. So there were 5 neutrinos. Of course I got rid of it. 1, 2, 3, 4, 5 different neutrinos to look for in the solar neutrino spectrum. So the proton-proton neutrinos, that's these ones down here, that's the dominant one. The beryllium-7 neutrinos, you have 2 different energies that the neutrino can come off with 2 different energies. That shows up as these lines. Okay, you have the PEP neutrinos, that shows up as this line, and then you have the boron 8 neutrinos, that's this spectrum, and the HEP neutrinos is this spectrum. So some of these neutrinos come off at very specific energies, and some of the neutrinos come off over a range of energies. So you have the HEP spectrum here, you have the boron 8 spectrum, you have the PP spectrum. So that's this one up here that's kind of less interesting because almost everything comes through there. This is a more interesting one because it gives you, it's sensitive to 1/4% of the interactions that take place. Anyway, so that's what you get. And then if you have some other nuclear processes are going to contribute to the spectrum that we see from the sun. Anyways, these are the important features to look for. The proton-proton, beryllium-7, PEP, boron-8, and so forth. So how do you detect a neutrino is a good question that people were wondering in the early 1960s. How are we going to detect these neutrinos coming from the sun? For one thing, the fluxes might be fairly high, right? The luminosity is going to be, for every photon that the sun emits, you're going to emit something on the order of a neutrino. But neutrinos have very small cross sections, so you have to choose carefully how you absorb those neutrinos and how you can tell if you actually caught something. So the way that you do that is you take a look at the periodic table. Since we're going to make your detector out of chemicals, you need to look at the periodic table to figure out what chemical elements do you want to have as your detector, because they're going to have certain processes. And these neutrinos are not going to be absorbed by the electrons. The neutrinos are going to be absorbed by the nucleus. And so when a neutrino gets absorbed, it will actually change the chemistry in the following way. So if we go to P table like this, when you absorb one of these neutrinos, you're going to convert the nucleus of whatever substance you have is going to convert from one material to another. And so if you choose wisely, you can make your life easy by having really different chemical properties between the substance you start with and the substance you finish with after the neutrino is absorbed. So there are a variety of other ways to detect neutrinos, but this is for the first detector that they made. So the first detector they made, if you want to have a very large difference in the properties of the chemical properties of the substance that you have, then it's useful to pick a noble gas, so one of these, as either the starting point or the ending point of your nuclear process. And then you have highly reactive things on either side of the noble gases. So you have this one here, the halogens, so fluorine, chlorine, bromine, iodine, astatine, Tennesseeine. Well, okay, I guess Tennessee gets to have its own element. So these ones, or you have something over here, sodium, potassium, rubidium. So these ones are all highly reactive. These ones are also highly reactive. Yang Sunny, I'll get to that one. Why don't you ask me at the end when I'm done with this part. Okay, so chlorine. Chlorine was the thing that was chosen. You start with chlorine, and then if you absorb one of these neutrinos from the sun, you will convert the chlorine to argon. And so you go from a highly reactive and pretty corrosive gas to a noble gas that is inert, and doesn't interact chemically with anything. And so they chose a substance that was filled, they filled some kind of container with a lot of chlorine, and they'd used like dry cleaning solution. So it had chlorine mixed in with it. It wasn't chlorine gas, it was chlorine, some kind of chlorine, something. We'll take a look and see what it was that they used, but it had chlorine in the chemical composition. And when a neutrino was absorbed by the chlorine, then it would convert into argon, and then they can cycle through this substance and count the number of argon atoms that come out. Yes, so they did dry cleaning solution, and this was all done at what's called the Homestake Experiment. So this is the Homestake Experiment in all of its power and glory, an actual photograph. So it's this big vat underground. They have a catwalk going around it. It's deep underground for reasons that I'll get to in a moment. So you can see that it has this netting up here to make sure that the roof doesn't fall on this worker that is supervising the conducting of this experiment. So the tank has been flooded at some point. It was flooded at some point. I don't know if they've actually unflooded this part of the tank. So this is a mine in South Dakota. The Homestake Experiment, sometimes the Davis Experiment, I've never heard it referred to as the Davis Experiment. And so astrophysicists Ray Davis and John Bacall. So John Bacall was at Princeton. He's no longer at Princeton. He passed away about 15 years ago. Ray Davis was awarded the Nobel Prize in 2002 because it turns out he was right, even though it ended up people thought he was wrong for several decades. Okay, so this is the shape of it in the mine. Like here's the vat of stuff that they had in there, and they have these pumps where they pump it out, and then they would test the chemicals, like look for the argon as it comes out from the from this, and then they pump it back in. So they're circulating the chlorine out of this thing to count the argon that is formed as it absorbs the neutrinos. Let's see, so what did they use? So here's the thing, they had the neutrino absorbed by chlorine, it turns into argon and emits this electron. The reaction threshold, now this is important because the reaction threshold will only take place if the neutrino has enough energy to cause this reaction to take place. So you will only get this nuclear interaction, it's kind of hard to see, but you only get this chlorine turning to argon if the neutrino originally has enough energy. And here it is 0.8 MeV. So if we take a look at the solar neutrino spectrum, 0.8 MeV is like right here. So that, this vertical line right there. So it will capture some of these beryllium 7 neutrinos, but it will only be able to detect the beryllium 7 neutrinos, the Hep neutrinos, and maybe some of these boron 8 neutrinos. The number of Hep neutrinos is way too small, right? This is 1,000 times less common than these boron 8 ones. And so here at the peak, that's 10 to the 3, this is 10 to the, so this is 1 billion times, you get 1 billion times more PP neutrinos than you get Hep neutrinos. However, the proton-proton neutrinos, that very first one that takes place in the proton-proton chain, this one that takes place up here, the energy that you get is around, what? Half an MeV? Is it? Yeah, about half an MeV, which is below the threshold. Where did it go? It's below the threshold to allow this thing to take place. So the detector in the Homestake experiment is not capable of measuring the PP neutrinos because they don't have enough energy to cause this reaction to take place. Argon has a half-life of 35 days. So once you form that argon, you have to detect it in 35 days or else it will spontaneously decay into something else. And so there had to be constant recycling of this material in order to count it. Davis bubbled helium through the tank to collect the argon that formed. A small few cubic centimeter gas counter was filled by the collected few tens of atoms. Few tens of atoms. So you have this gigantic swimming pool sized vat of dry cleaning solution, and you're getting a few tens of atoms, argon 37, to detect its decays. That's pretty cool. Tens of atoms. Okay, and it's mixed in with argon that just exists in things in nature, the ambient argon abundance that you have, because argon is the third most abundant element in the atmosphere. So you have nitrogen, oxygen, argon is third. So, anyways, he ran this. Let's see if we can see where it has perchloroethylene. Perchloroethylene was chosen. So let's take a look at that. Perchloroethylene, 100,000 gallon tank of perchloroethylene. This is tetrachloroethylene, which is, I guess, the new name for it. So there you go. It's 4 chlorines attached to something. So it's a dry cleaning solution. Hence, it's sometimes called dry cleaning fluids. And it's got a sweet odor because what could be better than that? So 2 carbon. Right there. So 2 carbons and 4 chlorines. And that's why you use it, right? So it's bound up. The chlorine is not going to like corrode everything because it's bound into this atom, but you can produce the argon out of it. So that is the design of this Homestake experiment, is to detect that transmogrification of the argon into chlorine. So they make this measurement. They have a prediction. They predicted, here's the solar neutrino spectrum. It looks like this. It's got these lines. It's got this thing over here. It's got another line. And they were able to detect everything from, this way north. So they could detect all these neutrinos that are up here. So this is energy of the arriving neutrino. And this is the flux, like the total of neutrinos that arrive. So they should be able to detect all these neutrinos that are coming up here in their experiment. And so they made a prediction. If the sun actually shines through these processes the way that we expect that they would, then we would expect, let's say, 100 neutrinos per whatever. 100 neutrinos, they're probably detecting a couple neutrinos a day is the way that this works. Okay, so so 100%. Like if it matches the predictions, then they would get 100% of what they would expected. So they ran this experiment, and it turns out that they got something like 50%. Okay, or a little bit less than 50%. And that was a problem. That was not what they expected to find. It was less than half. Was it this experiment where they saw 30%? One of them they saw 30%. So let's see. Turned out the discrepancy, calculate the rate which the detector should capture neutrinos. We got that. The discrepancy in results created the solar neutrino problem, and it doesn't say what the fraction was. So let's see if we can find it here. Observed in the mid-1960s, right? So this experiment was built in the 1960s and was finally resolved in 2002, like less than 20 years ago. Just barely less than 20 years ago, but still 20 years ago. The issue was with the Homestake experiment, it doesn't say what they measured, but I think that the Homestake experiment measured 30% of, that's my recollection is that it was actually 30%. There were two later experiments that I will talk about. So it was basically a third of the experiments that they expected to find. Yeah, so they found 1/3 of the neutrinos that they expected to find in this, and that was a big problem. And so for a while, everyone was like, well, you don't really know what you're doing. We particle physicists, we understand what we're talking about because when you create these neutrinos, they stay the way that they are and they don't change. And so because we're particle physicists and you're just a lowly astronomer, you don't know what you're doing, and therefore it must be something wrong with your experiment. And so they ran for a long time a whole bunch of different calibrations. What if we just bring in a radioactive source and put it in there? What if we put a little bit of argon and mix it into the thing? We'll be able to detect it the way that we want to. So they did a bunch of things to calibrate their instrument to make sure that they were counting everything properly. And they kept coming up with, like, we know what we're doing, like all of our backup plans are detecting things the way that we expected them to. Our systems are functioning properly. A bunch of astrophysical theorists started creating new models for maybe how the sun shines. Maybe the sun shines differently. Stephen Hawking, of course, said, well, maybe there's a black hole in the center of the sun and it's shining through some magic from the black hole. So the theorists kind of went wild trying to come up with different ways for explaining, maybe we don't understand how the sun works, because the particle physicists have told us vehemently that their particle theory is correct and that it can't possibly be wrong. And therefore the problem must be on the astrophysics side, either in the experimental side or on the side of our theory about how the sun shines. Maybe the sun doesn't shine the way that we think that it does. So the astrophysical theorists kept devising new, like, other solar models, like how could the sun maybe shine differently and to produce the light that we see, because you have to be able to produce the light that you see. And then when you do that, what does that cause for the solar model? So let's say that you change the way that the sun shines. Okay, let's say that the sun shines the following way. You come in here, you still have a core where you're fusing, you're still doing the proton-proton chain in here, and you're still producing the neutrinos that come out, but this is only 1/3 of the luminosity. So the sun shines 1/3 the way that we expect it to, and maybe there's a layer of unicorn poop or something like that. So there's a layer of unicorn poop in the sun, and that unicorn poop is producing light in its own right, and that's the other 2/3. So you have 2/3 of the light from the sun is coming from this magic layer that's producing stuff somewhere else. Well, that changes the density profile of the sun. Okay, you're going to have some density profile. The density of the sun is going to change as you come up here. Then you have an energy source, and whenever you have an energy source, that's going to cause things to expand in that area, which is going to reduce the density and change the temperature. So you're going to have a temperature profile, a density profile of the sun, and then you have the core down here. And so you're going to have different sources of energy, which is going to change the way that the sun looks like on the inside. Okay. Fortunately for the astronomers, there are more ways than one of studying the interior of the sun. Now, studying how the sun shines is one thing. Like the nuclear processes that go into making the sun shine, that's one thing. But actually understanding the structure of the sun is something else. I even have a container of the unicorn poop. See right there, and it's space unicorn poop, right? Because you can see through it. So unicorn poop, right there, brought to you directly from the sun. All right. So what happens is we can study the interior of the sun. So the interior of the sun, we study it the same way that we study the interior of the Earth. The sun shakes. So here's the sun. It's shaking. Like this is an artist's rendition of the sun shaking, and those sound waves are going to propagate into the interior of the sun, and the speed that they propagate depends upon the density and temperature and behavior of the sun at different levels. So if you have like a convection zone, and there is a convection zone near the surface of the sun, you're going to have sound waves that bounce back and forth between the convection zone and the next layer underneath it. You're going to have things refracting off of the different layers in the sun. You're going to have sound waves that go deep into the sun and come back out. Okay, so the density profile of the sun is going to determine the frequency of the oscillations, the frequency of the vibrations that the sun has going on. So if we take a look at the interior of the sun, if we look at like, let's pull up something else, like this solar interior here, you can see that there are different sound waves, and we can measure the oscillations of the sun. So if we look at the sun solar oscillation spectrum, so the sun is constantly pulsating. If you look at the solar oscillation spectrum, this helioseismology, hopefully we actually see, so this is how you would decompose the sun. You don't decompose it into heel picks the way that we talked about earlier. You decompose it into basically the electron orbitals, the shapes of the electron orbitals is the way to do it. And then there is no, okay, so here's the power spectrum. This is how the sun shakes, power spectral density, and you can see this bump right here. That bump, if you zoom in on it, then you get the information that I want to show you. So here is these bumps, different frequencies of sound waves. You basically have standing waves bouncing back and forth in the interior of the sun, and they oscillate at certain frequencies. And there's, they have this, so I'm not a helioseismologist, but there's a gap, there's like two different frequency gaps. There's this wide gap between these ones, and then you have a narrow gap between like these side bands. I don't recall exactly the physics that describes these. That'll have to be for a different stream. I'll have to go back and research the different kinds of oscillation modes that you get. So they're going to have these oscillations, and the structure of those oscillations are going to tell you about the density of the interior of the sun, what the sun looks like in terms of the profile that you get. Okay, so as the improvements occur in our understanding of the interior of the sun through helioseismology, the constraints on the kinds of solar, like how the sun can shine, become tighter and tighter and tighter. And eventually you get to the point where you just can't have unicorn poop anymore. So it turns out the unicorn poop model did not work. The black hole model didn't work. All these other solar models didn't work, and it kept forcing you back to the nuclear physics. It kept forcing you back to the idea of the proton-proton chain, where this really must be how the sun generates its light, because any other option that we come up with doesn't produce the right amount of energy, or it produces the wrong density profile, and we keep measuring these things. So that forced people to look more closely at the neutrinos we get from the sun. What happened then is in the late 70s and early 80s, there were a handful of new experiments that were built. Let's see, the experiments, I'll use this one. These are SAGE and GALEX. So SAGE, which changed, it used to be the Soviet American Gallium experiment, and then it changed to the Russian American Gallium experiment as it spanned across the falling of the Berlin Wall. So, and GALEX, both of these, so GALEX was an Italian one at the Gran Sasso laboratory. So Gran Sasso is a cave in the Apennines, I think. Let's see, Gran Sasso, so here's the mountain. The largest underground research center in the world. I think that will be supplanted by the laboratory that the United States is building in the Homestake Mine, where the original solar neutrino experiment was run. That mine was eventually abandoned, and then they filled it with water. Well, it filled with water. And then they built DUSEL, which is the Deep Underground Science and Engineering Laboratory that's being built right now by the Department of Energy. And so they drained out the Homestake Mine and are rebuilding new stuff there. Okay, so Gran Sasso, anyways, I think it's in the Apennines, like the mountain range that runs right through the center of, it's 120 kilometers from Rome, so it can't be all that far. Anyways, so the Gran Sasso mine, can we look it up here? Is it going to show it? We want to see where this thing is located. Oh, that's no help. I want the, well, anyways. You'll just have to trust me, I guess. Maybe this will have it on a map. Yeah, okay, so there it is. There's the Apennine Mountains that run along the length of the boot of Italy, and it's right there, L'Aquila, which I think means the eagle, because Aquila is the eagle constellation. All right, anyways, so Galax was the one that was run at Gran Sasso, and Sage was this Russian-American one. I think it was done in the Caucasus, but I may be wrong about that. We'll take a look real quick. Anyway, Sage and Galax. These were both designed to measure in the Caucasus, at the Baksan Neutrino Observatory in the Caucasus Mountains in Russia. At the time of the Soviet Union, but all right. Now, the reason that gallium, so both of these use gallium, and what they are looking at is this interaction. Gallium goes to germanium. Gallium goes to germanium. So if we look at the periodic table, right here, gallium is right here, and germanium is right there. And they do have different properties, right? They're as different as aluminum and silicon are from each other, or as boron and carbon, or as indium and zinc, or indium and tin. So gallium and germanium do have different chemical properties. They kind of span the transition metals. And so you start with a gallium substrate, and then you absorb a neutrino, and that converts you into germanium. And then you can detect when that chemical transition has happened because of the different chemical properties between these two things. The advantage of using gallium and germanium is that, unlike with the chlorine argon, the gallium and germanium have a lower threshold. Okay, so it's on the resulting germanium is unstable with a half-life of 11 days instead of 35 days, but that's something that you can deal with. Once a month, the neutrino-induced germanium is extracted from the gallium, so you lose some of it because you do it once every 3 half-lives, but it's still you can still detect it. And does it say what the operating threshold is? The point being, the reason that they did it with gallium is that you're sensitive to more of these neutrino interactions. If we look at the solar neutrino spectrum and we compare it to the sensitivity of these different things, you can look at this one. So this is the original prediction. For what detectors would be capable of detecting which neutrinos. Okay, so for the lowest energy neutrinos, you're able to detect with, so chlorine, which was the first experiment, was here, right? That's the 0.8 MeV, right? So chlorine would be able to detect these beryllium-7, the PEP neutrinos, and some of these boron-8 ones. So that is the neutrinos that they would be sensitive to from this. The gallium experiment is sensitive to things that are, like a third the energy. So from way down here, it's able to detect these PP neutrinos. It's able to detect the beryllium-7 neutrinos, this line of the beryllium-7 neutrinos. So it's sensitive to a lot larger flux of neutrinos. It will detect way more neutrinos than the chlorine experiment does, because the chlorine experiment is looking at these neutrinos where you have like 10 to the 4 per second or something like that, where the PP neutrinos is 10 to the 11. That's 10 million times more neutrinos of this. So you're sensitive to a larger volume of neutrinos coming from the sun if you switch from chlorine to gallium. That's why they did the gallium experiment. So they're sensitive to these things, and then they made the measurements and they got 50%. They saw 50% of the stuff that they expected to find. So the chlorine saw 1/3, these gallium experiments saw 50%. And so it was really a big problem. The solar neutrino problem, we don't know how we can't verify that the sun is shining the way that our models and our understanding of nuclear physics predicts that it should shine. And then you have this water one up here. So water, the way that you detect neutrinos in water is by Cherenkov radiation. What happens is so here's a bucket of water, okay? Light in the vacuum travels at 300,000 kilometers per second, okay? Light in water, so here's a light ray coming in. When it gets to water, it slows down as it moves through the water. In water, light travels at 200,000 kilometers per second. It's like a little bit more than that, 230,000, something like that. I guess it'd be 1/4 shorter. Anyways, so let's say that the point being it's less, right? So 230,000 kilometers per second is how fast light travels here, which means if you have an electron coming in slower than the speed of light out here, so here's your electron, and it's coming in at, let's say, 270,000 kilometers per second, which is slower than the speed of light, but it's going to hit this water, and it can travel faster than the speed of light in the water. So the speed of light here is a lot slower because of the index of refraction of the water. The electron comes in wicked fast, going faster than the photons that it's passing by, and as a consequence, it starts emitting light of its own. It starts emitting what's called Cherenkov radiation. Cherenkov radiation. Okay, so Cherenkov radiation is radiation emitted by charged particles when they're moving faster than the speed of light in some medium. So in the atmosphere, particles can travel faster than the speed of light because the atmosphere slows down the speed of light, not by much, but by a little bit. And in water, it slows down a lot, so you can get Cherenkov radiation. You can see what Cherenkov radiation looks like if you have a nuclear reactor handy, because some of the particles that come off of nuclear reactors are traveling faster than the speed of light. So if we look at Cherenkov radiation, this is what it looks like in a nuclear reactor. Okay, so this blue light that comes off is light emitted by particles traveling faster than the speed of, charged particles traveling faster than the speed of light in water. So that is Cherenkov radiation. It's pretty cool looking, and you get it from those kinds of things. So when you make a water detector, when you're looking for neutrinos coming from, where did the thing go? I think I deleted it to get to, oh, here we go. So when you make a water detector, you're not sensitive. It takes really high energy neutrinos in order to produce electrons moving fast enough to detect that Cherenkov radiation. So water detectors are only sensitive to really high energy neutrinos. They're not sensitive to these low energy ones that you get from the chemical stuff. So this kind of set the stage for neutrino experiments that came later. So we started with the chlorine experiments back in the 1960s and 1970s, then the gallium experiments in the 80s and 90s, as they were trying to resolve the solar neutrino problem. Why is the sun emitting only a fraction of the neutrinos that we expect to find? So that is the original gallium experiments that set the stage for the Nobel Prize discovering what ended up being neutrino oscillations. So we will cover neutrino oscillations at a different time. I do want to show an image of what these Cherenkov detectors look like, what these water detectors look like, and we'll go into detail about how they operate on another stream. So let's see, if I want to go to SuperCamioconde Conde Experiment, this is what the Cherenkov detectors look like. Okay, so we'll use Symmetry Magazine. So they're filled with water. Here's some workers who are cleaning the photomultiplier tubes. So these are all photon detectors around that perimeter. Here's these workers. They raise it up to a level. They float around. They clean all these things as they go. Hopefully they keep track of where they're located, so that they don't end up cleaning too many of them twice. And then they fill it with water. And this chamber is gigantic, right? You can see how big it is, and you can't see the top and you can't see the bottom from where you're located. So this they fill it with water, and then when the neutrinos come from the sun, only a small fraction of them will be absorbed by anything, but they'll be absorbed by they'll hit the water, send an electron off at very high speeds. That electron will create a shower of Cherenkov radiation, and then these photomultiplier tubes will detect that Cherenkov radiation. So it's the neutrinos basically slam into stuff, and it takes high energy neutrinos to slam into stuff and move the electrons fast enough so that they're going faster than the speed of light in the water. Now, one of the other things that I said I was going to talk about that I didn't, and so I will do it now, is that all of these detectors are built underground. So you have the Homestake experiment that was built in the Homestake Mine. If we pull up the map, that was built in the Homestake Mine. The reason you want to get it deep underground is because there's a bunch of stuff coming in from the atmosphere. There's radon near the surface of the Earth. There's all sorts of background noises that you get, or background signals that you can get from stuff near the surface of the Earth. You have cosmic rays coming in, hitting the upper atmosphere, causing all sorts of problems. And you don't want those to confuse your signal that you're getting from the sun. So you bury it deep underground to eliminate the stuff that happens at the surface, because it's hard for charged particles to penetrate through rock. Neutrinos can penetrate through rock without any trouble. The neutrinos don't even notice really that the Earth is there. But because only 1 out of every bazillion is actually absorbed by anything, including your detector. But it eliminates atmospheric muons. It eliminates radioactive sources near the surface, and so getting it deep underground allows you to control the background environment so that you can detect the few instances per month where you're gonna, or a few instances per day where you're gonna have this transformation go from the absorption of the neutrinos. So if we look at Homestake Mine, South Dakota. So this is the Homestake Mine where the original experiment was run, right there. But it's an underground mine where they ran it, not a surface mine. So there you go, South Dakota, and that's so now they have DUSEL, the Deep Underground Science and Engineering Laboratory. I don't think it's been completed yet. But it's also in that same place. It's going to be deeper. The deeper you go, the more backgrounds you eliminate, and you're going to have a large scientific. So instead of a lead mine or whatever the mine was, instead of a mine to get metals out of it, it's just going to be a scientific laboratory that's deep underground. So there you go. That is the original neutrino experiments up through the 1990s, and we'll see the conclusion of this. I guess I'll do the conclusion of this next time.